And so now we come to problem number 2, which is a classic. I want you to really pay attention to it, and in any case, you should be able to do this problem cold at the next exam. Problem number 2, 2328. We have a conducting shell. It's a metal. This is the metal. The inner core, vacuum, radius A, and the outer shell has radius B. And there is, right here at the center, a point charge plus Q, and here at the outer surface is a total charge of minus 3Q. That total charge undoubtedly is uniformly distributed. Whether you like it or not, that happens automatically when this is a metal. All right now. Now you're being asked to calculate what the electric field is everywhere here in space. Here, here, and there. Now there's no charge inside the conductor, because any charge inside the conductor would make the electrons experience a force, the electrons would start to flow, and they would kill the electric field. So already for R less than B and larger than A in the shell, we know that the electric field equals 0. So that's easy. What now is the situation for R larger than B? I take a Gaussian sphere. You have to always work with symmetry. So you bring a concentric sphere here, and this concentric sphere has a radius r. Let us assume, it could be wrong, that the electric field is pointing outwards. It is certainly going to be radial. It has to be radial for reasons of spherical symmetry. And of course the surface elements ds, the surface integral, not integral, but the surface elements ds will all be everywhere perpendicular to the surface, no matter where you are on the sphere. So what is Gauss's law? Telling us now that the closed surface integral of E is a dot product with that ds, that is the total charge inside the sphere divided by epsilon 0. Well, E is everywhere the same in terms of magnitude on this sphere, and so the dot product we will take plus 1, because we will make the assumption that they are in the same direction. If the assumption is wrong, we will quickly find out. So I find 4 pi r squared times E equals the total charge inside. This is minus 3Q plus Q is minus 2Q divided by 4 pi epsilon 0 r squared. No, 2Q, I'm getting ahead of myself, epsilon 0. Total charge inside divided by epsilon 0. And so what do I find for the electric field? The electric field then becomes minus 2Q divided by 4 pi epsilon 0 r squared. And if you really want to get the direction right, this minus sign means that my assumption was wrong, so it's pointing inwards. So you can put an r roof here, which means, you know, this minus is winning over the plus, so the electric field is pointing inwards. If now you want to know what the magnetic field, the electric field is inside the inner cavity, then again you apply, here is that radius A, you again apply a spherical surface with radius little r, and you yourself can now very easily convince yourself that inside this cavity the electric field will now be plus Q divided by 4 pi r squared epsilon 0 r roof. So the E field is now not pointing inwards, but the E field is here in this cavity pointing outwards. And notice that when r equals 0, right here you get an infinite value, which of course physically has no meaning. I would like to make a drawing, which is very useful, I think, of the electric field. I don't think you're being asked to do this, but it's always very useful. The electric field as a function of distance r from the center. Here is location B, and here is location A. So we know that right here we have a magnetic field which is minus 2q divided by 4 pi epsilon 0. R squared becomes now B squared, because I'm at the location B, and then it falls off to 0 proportional to 1 over R squared. Then inside the shell, inside the metal, there cannot be any E field, so it drops to 0. There's a discontinuity here. And then inside the cavity, it increases as 1 over R squared, and it goes here to infinity for R equals 0. Now we are being asked about the induction charges. If I have here the inner cavity, radius A, and charge plus Q here, then I know that the electric field anywhere here in the metal is 0. So if I take some Gaussian surface R prime, which is slightly larger than A, and I apply Gauss's law, then I find that 4 pi R prime squared times E must be 0, because E is 0. And therefore it follows that Q inside must be 0. But how can Q inside be 0? Because there is a plus Q here. Well, the only way that nature can do it, that nature induces now on the inside of the inner sphere a total charge of minus Q, so that the net charge inside this sphere is 0. And similarly, you can calculate the induced charge on the outer shell. I'd like you to do that to be consistent with the electric field that we just calculated. It's a very important problem. You have to fully understand this, and as I said, make sure for next exam that you can do this blindfolded at 3 a.m. in the morning if I were to wake you up. Very well. Now we want to know the electric potential everywhere. How is electric potential defined? VA, the potential at A, minus the potential at B, is the integral in going from A to B of the electric field vector dot dl over some path length L. So here is point A, and here is point B. Here is some crazy routing. Here is a little vector dl, and at that particular location the E vector is like so, and everywhere along the path do I have to calculate that dot product E dot dl, and I have to integrate that over the whole path. That is the definition. Very often do you see in books that it is minus the integral in going from B to A of E dot dl, and that of course is exactly the same thing. We often, when we can, define the electric potential at infinity 0. It's not always possible, as you will see in the future, but whenever we can we do that. It's just convenient. With gravity we had a similar situation, that gravitational potential, it didn't matter what you call 0, whether you call the ground floor 0 or the surface of the table 0, it doesn't matter. And the reason is that it is the difference in potential that determines what the actual physics will be doing, and not the absolute value. So if I go from point A in some crazy way to point B, and if the integral of E dot dl along this path is independent of how I'm going, then the potential difference, VA minus VB, is uniquely determined, and we call the electric field then a conservative field. If, however, the potential difference, or I should really say if the integral E dot dl depends on the routing, then the electric field is non-conservative. And it's very hard to imagine what that can be, but you're going to see this in the future with Faraday's law, and almost no one has any intuition for that. And the whole concept of potential difference is then not even defined, because the integral E dot dl from one point to another depends on the routing. Gravitational fields are conservative, because again there it doesn't matter how you move from one point on the table to a higher point. But friction is non-conservative, because if I have here point A and I have here point B and I move my finger this way, I experience a frictional force. Well, if I go along a straight line, the work that I have to do to overcome that friction is less than if I made this enormous side track. So friction is a non-conservative force. If you multiply delta V, electric potential, with a charge Q, then you get energy. In a similar way, if you multiply the gravitational potential, which I will define now as GH, if you multiply that with a mass, then you also get energy. So you see the electric charge Q in electricity plays the same role as the mass in gravity. And one could call then this the difference in electric potential and this the difference in gravitational potential. H is the vertical distance between the 2 points that you are considering. Let's now go back to our problem, and we want to know what VA minus VR is. We have let me make sure that I have that you have the geometry right. Oh yeah, we have here the radius A, and we have here plus Q. And we want to know what VA minus VR is, and we want to know that everywhere in space. VA minus VR, let's call this R. So what is the potential difference between, no, this is not what I meant. I meant this point to be A. My shorthand notation is this point A, potential difference with this point R. Well, this is a metal, so there is no electric field. So the potential difference between the surface of the inner cavity and any point in the metal equals 0. What now is the situation when I am anywhere between A and B? Well, again, E then must be 0, because it's 0 everywhere in the metal. The metal is an equipotential. What now is the potential difference between a point B, say here, I call this point A, at the surface B, and some point P, which is at a distance R from the center? What now is VA minus VP? Well, the electric field is pointing inwards. We just calculated that. It's a function of R. It falls off as 1 over R squared. And so it should be immediately obvious that VA must be less than VP. If I take a plus charge and I release the plus charge will move in this direction. And the plus charge always moves from a higher potential to a lower potential. That's something that you really should remember. When you're in doubt, you take a plus charge, you release it, it will move in a certain direction under influence of the electric force. It always goes from a higher potential to a lower potential. Whereas a negative charge, so to speak, flows upstream. It goes from a lower potential to a higher potential. So you already see that VA must be lower than VP. What is the difference between here and here? Well, there is a neat way to do it, and there is some kind of a dirty way to do it. The dirty way would be to say, okay, I take the integral from A to P of E dot dl, I will call dl in this case dr, and I don't worry about minus signs, I don't even worry about this dot product, because the dot product either produces a +1 or a -1. I just do a very dirty integration job without worrying about signs, and if it then turns out that VA is not smaller than VP, I just cheat and put a minus sign in front of it, and I think no one can blame me for that, because I know in advance that VA must be smaller than VP. Now, if you want to do it the elegant way, the neat way, which of course is a little longer, then it goes as follows. So now we are larger than B. The electric fields, I go now through a complete vector notation, equals minus 2q divided by 4 pi epsilon 0 r squared r roof. Would you agree? It's pointing inwards. And of course I will write down for dl, I will write down dr. So the integral from point A to point P of the E vector dot dr can now be written as minus 2q divided by 4 pi epsilon 0 times the integral in going from location r equals B, that was that point A, to r equals R, that was that point P. And now notice carefully, R roof dot, I shouldn't forget the dot, dr, which is also a vector, divided by r squared. This is nothing but dr. It is plus dr. I hope you can convince yourself of that, because r roof and dr are in the same direction. In other words, I will have to only evaluate this integral dr over r squared. And that equals minus 1 over r between B and r. And so that equals 1 over B minus 1 over r. And this value is positive, because B is smaller than r, because r was outside B. And so this is the neat way to do it, the elegant way. And so you'll find now that VA minus VP equals minus 2q divided by 4 pi epsilon 0 times 1 over B minus 1 over r. Potential has no direction. It's a scalar. We express it in terms of volts in MKS units. And when you go to infinity, when r goes to infinity, in this case V goes to 0. And so if you want to know what exactly the potential is at that location A, which was at that radius B, then you'll find minus 2q divided by 4 pi epsilon 0 times 1 over B. This now is the potential at the outer surface. I would also like to make a drawing of the potential as a function of r. It always helps. It gives you some insight. So here is the potential V, and here is the radius r. I have here the outer shell B, and here the inner shell A. Well, the electric potential here we know equals minus 2q divided by 4 pi epsilon 0 B. We just calculated that. And then it falls off as 1 over r, proportional to 1 over r. In the shell there is no electric field. If there is no electric field, it must be an equipotential. So the potential is everywhere the same, so it remains this value. And now you go inside the sphere, and that's the part where I think I want you to show that. Now the potential will increase again. And I'll bet you anything that it will also increase as 1 over r, and it will go to infinity at r equals 0. So I want you, with a Gaussian surface, to calculate what the potential is for r is less than a and r is larger than 0. What you see here is something interesting, that there is one spot inside the inner cavity where the potential is 0. And I would like you to calculate at what r that occurs. I did it, I may have made a mistake, and I found when r equals ab divided by 2a plus b, that right there the potential is again 0. So if this is that inner cavity, which has radius a, then there is here somewhere a radius where the potential everywhere is 0. All right, potential difference is connected with work. When I put a 1 Coulomb charge in my pocket and I move from one potential to another, then if I go from a lower potential to a higher potential with the 1 Coulomb in my pocket, I walk uphill, I have to do positive work. If I go with the 1 Coulomb in my pocket from a higher potential to a lower potential, I have to do no work, I have to do negative, I shouldn't say no work, I have to do negative work. The charge moves all by itself under influence of the electric field.